On Warren Peak in the Rockies, a nuclear power plant is serving the Air Defense Command radar station near Sundance, Wyoming. It is the PM-1 air transportable nuclear power plant designed and manufactured by the Martin Company. PM-1 is a joint undertaking of the Department of the Air Force and the Army Nuclear Power Program, a part of the Atomic Energy Commission. The PM-1 reactor, a compact pressurized water system, first went critical on the 25th of February, 1962. By midsummer, it was producing the 1,000 kilowatts of precise electric power needed by the 3 huge radars of the Sundance Air Force Station. These radars are under protective radomes to shield them from high mountain winds and heavy snow. PM-1 will also supply steam to heat the entire radar installation. 7 million BTUs per hour, heat for the operations building, where the radars paint their picture of the sky. This picture is relayed to the Air Defense Command. PM-1 will heat the shops, which keep the radars working, as well as the station's communication equipment and other supporting facilities. The installation is in remote country. Sundance, Wyoming, the nearest settlement, is 6 miles away. At Warren Peak, neighbors are few. PM-1 was placed here to prove that it could function in isolation, in a climate nearly as rigorous as that at the poles. At 6,000 feet above the sea, the temperature ranges from highs of 87 degrees Fahrenheit to lows of -50. But the radars must read the skies in any weather. And PM-1 will furnish them power for 2 years from a single nuclear fuel loading. This reduces the need for heavy logistic support. Supplies reach the base by road, 93 miles overland from the railhead at Rapid City. The basic plant was assembled at the site from 16 packages. It could be relocated the same way. 4 packages contain miscellaneous equipment, but the heart of the PM-1 is in the remaining 12 packages, divided into the primary and secondary systems. The primary system is made up of 3 of these packages. There are 4 tanks, reactor, steam generator, and spent fuel core tanks grouped together. The radioactive waste disposal tank is a part of the 3rd package. It is shipped in the spent fuel tank. The secondary system contains 9 packages. The control room package contains the console from which the plant is run by a single controls operator. These controls must meet a reliability specification of 99.45%. Consequently, solid-state components are employed. The turbine generator package houses the equipment that converts to electrical energy the heat generated by the reactor core. The generator produces 1,250 kilowatts gross output. Equipment in the switchgear package works with the generator to refine this output and to give the plant one of its most striking design characteristics, the high quality of the electricity produced. This quality is governed by a voltage regulator and static exciter, which can eliminate the need for further electrical refinement. With these units, electrical variations are held to tight tolerances. Voltage varies less than 2%. Frequency, less than 2%. Harmonics, less than 2%. The heat transfer equipment package is made of 2 units. One contains the evaporator reboiler, which manufactures the low-pressure steam for space heat. The other unit is conventional heat exchanger equipment. 4 direct air-to-steam condensers account for 2 packages of the system. They cool the steam from the turbine by drawing air over the condenser piping. No cooling liquid is involved. This type of condenser was selected so that the plant can operate in an area with a low water supply. The maintenance package holds standby generating equipment and a shop with a grinder, welder, and lathe. Almost any general repair to the plant can be made here. By specification, the plant can only be shut down 21 days per year, and of these, only 6 are scheduled for annual plant shutdown. The shop will help the plant to meet its shutdown specification. A separate building holds the 9th package of the secondary system, the Decontamination and Water Chemistry Unit. Here, too, health physics sets its line of demarcation, establishing the contaminated and clean areas. Personnel crossing this line from the primary system are given a radiation count. We are now ready to look at the design of the system in some detail. "741 nuclear fuel tubes make up the reactor core. These tubes are grouped into 7 fuel bundles, 6 peripheral and a center bundle. With the proper tools, we can fuel and refuel the core as a whole. Or, if necessary, we can replace individual bundles without removing the entire core. The core, a thermal shield, and an upper skirt are enclosed in a pressure vessel. Primary water flows into the pressure vessel, down around the core, cooling the thermal shield. This water then passes up through the core, absorbing heat, and flows out the holes of the upper skirt. The primary water is conveyed to the tube side of the vertical steam generator. It is pumped back by the primary coolant pump at a rate of 2,125 gallons per minute. Water leaves the reactor at 479 degrees Fahrenheit. It returns to the core at 447 degrees. A 32-degree rise in temperature means that the reactor generates nearly 35 million BTUs. A pressurizer maintains the system at 1,300 psi to prevent boiling. As the primary water flows into the tube side of the steam generator, it gives up heat and flows out. Secondary feed water picks up that heat on the shell side and is released as dry steam. This steam drives a single extraction turbine generator and feeds the evaporator reboiler at the same time. Exhaust steam from the turbine flows to 4 air-to-steam condensers and is converted to water, which is drained to the hot well along with the evaporator condensate. The remainder of the secondary loop is somewhat conventional, having the necessary pumps and heat exchangers to recycle feed water back to the steam generator. The fuel elements are basic components of PM-1. Their manufacture starts our survey of PM-1 fabrication and testing. The fuel element tubes are approximately 1/2 inch in outside diameter and 33 inches long, of which 30 inches is of fissionable U-235. We begin with the uranium powder. Each fuel element tube contains 40 grams of enriched uranium-235. It is mixed with powdered stainless steel and formed into a rough cohesive sheet. After the sheet is sintered and enclosed with stainless steel foil, this is heated and rolled. This is the cermet meat of the fuel element. The sheet is formed into tubes in several steps. After its seam is closed, it is given inner and outer stainless steel cladding. The assembled tube is bonded and strengthened by drawing and isostatic pressure techniques. Tubes were assembled into the core configuration and tested in the company's critical facility. Critical tests at 0 power were used to check out the nuclear efficiency of various core configurations. and to test control characteristics. The chain reaction has begun. A test configuration of the PM-1 core achieved criticality for the first time on March 17, 1960. These criticality tests gave engineers the basis for refining their design of the core configuration and checked out the effectiveness of the components that control reactivity in the core. The final configuration contains 741 fuel elements. Its diameter, just under 2 feet. Its active length, 30 inches. Its overall length, 33 inches. 90 boron poison elements are permanently installed in the core. These burnable elements absorb surplus neutrons released by the fission process. They decrease the reactivity of the operating core to a controllable level. Y-shaped control rods start, stop, and control the rate of reactivity. The Y rods contain europium oxide, stabilized with titanium oxide, and mixed with stainless steel powder to form a cermet. There are 6 of these rods in the core. When all of the 6 rods are fully inserted, the reactor is subcritical. Fission cannot take place. As a safety margin, the core is subcritical with only 5 rods fully inserted, or even with 4 rods inserted and 2 in the operating position. When all 6 are withdrawn, a point is reached at which the reaction is slightly supercritical. Then the rods are repositioned at the critical point to hold the level of reaction constant. When the rods are reinserted fully, the reactor becomes subcritical, shutting it down. The rod movement is controlled by magnetic jacks. When coils in these jacks are energized, they hold or move the rods. When energized sequentially, they move the rods by increments. Gravity and springs in the top of the rod housing will drop the rods if the current is cut. Loss of current scrams the reactor, a fail-safe feature. Moreover, these jacks require only static seals, mainly on the pressure vessel head. No part moves against the seal, so the likelihood of leakage is minimized. As we've seen, pressurized water in the core acts as a moderator of neutrons for the fission process. The same water transfers the heat generated in the reactor to the steam generator. With this quarter-scale flow test, engineers studied the patterns of water moving through the reactor. PM-1 packages have been designed so that all welding is done at the factory. Field welding is eliminated because flanged fittings will be used for connections to be made at the site. PM-1 was completely packaged at the contractor's plant. The packages were interconnected and tested before shipment. All 16 packages of the PM-1 system are built to withstand the stress of airlift. The package dimensions are 8 feet 8 inches by 8 feet 8 inches by 30 feet long. The maximum weight of the packages has been set at 30,000 pounds, set on the basis of the permissible load that can be carried on a C-130 aircraft on a 1,000-mile mission. Air transportability of the system was flight tested during the spring of 1960. This airlift was a high point of the Air Force participation in the PM-1 project. The Air Force also contributed project officers to the program and tested the system condensers in the environmental hangars at Eglin Air Force Base. Beginning May 29, 1961, C-130 aircraft flew PM-1 packages to Ellsworth Air Force Base, South Dakota, for the overland trip to Warren Peak. The PM-1 was reassembled at the site on previously prepared foundations. The 4 tanks of the primary system were erected on foundations 30 feet below floor level. Backfill of crushed rock is packed around the tanks as a shield to reduce radiation to a safe level. Once package interconnections were complete and the core had been installed, pre-startup checkout and testing was accomplished. Subsystems were aligned in preparation for PM-1 to take over its role as power plant for the site. The auxiliary systems have been started and we're ready to go critical. The rods are withdrawn in pre-calculated amounts, and we watch for the start of a chain reaction. The reactor period is oscillating from positive to negative each time the rods are withdrawn. Now it remains slightly positive. We are critical. We adjust the control rods to establish the proper heating rate. The coolant water is continuously sampled so that its chemical balance can be corrected. We are up to operating pressure and temperature, ready to generate steam. Steam to the turbine. We have the turbine up to speed. Now, apply field voltage to the generator and adjust it. Power on the tie line. PM-1 is in operation. 2 men can operate this plant. 1 man monitors the plant's operation at the console, and the other continually inspects the working parts. The entire PM-1 crew has been trained for every conceivable situation arising in normal operation, in emergencies, or in maintenance. PM-1 is a safe system. Safety is built into the fundamentals of the design. PM-1 is a pressurized water system. If the water moderator in the reactor is overheated, it must expand, and when its density decreases, it loses its ability to support the chain reaction. The reactor will shut down. The reactor's controls are fail-safe. If current is lost, the rods will scram the reactor. The instrumentation continuously monitors 68 points in the system: temperatures, pressures, and radiation. Solid-state components ensure a high order of reliability in this instrumentation. The reactor safety system, which can warn the operator of potential trouble, also incorporates the scram logic circuit. This is a self-monitoring device that watches for 13 specific combinations of conditions. Its function is instantaneous action. For example, in 5 sets of conditions, it may lock the rods so that they cannot be withdrawn further. Or if the reactor exceeds 125% power, the circuit will scram the reactor. The crew has been thoroughly drilled in safety until emergency procedures and corrective action are automatic. A single PM-1 core will furnish full power to the radar site for 2 years. During this time, the Air Force, the Atomic Energy Commission, and Martin will scrutinize PM-1 operation. We will discover ways to extend the power range to increase the usefulness of such plants. Meanwhile, the first of a series of closely related systems, PM-3A, is being tested in the Antarctic. Compact and self-sufficient portable plants installed in remote regions difficult to supply are pioneers. PM-1 and its small crew is proving the safety and practicality of the medium-range reactor power plant. PM-1 opens the frontier for many new applications of nuclear electric power, both military and civilian.